Okay, so in this video, I'm going to talk about the center of momentum frame. So you may be wondering, hey, wait, didn't we just cover the 1D elastic collision, right? Why are we suddenly going to the center of momentum frame instead of going to 2D first? And the reason is because that 2D elastic collisions, it turns out is quite monstrous, right? But however, if you consider the center of momentum frame, right, then the 2D elastic collision becomes really simple. So as much as I like to have some continuity where I go from 1D to 2D, right, that seems to flow better, but I need to insert this center of momentum frame in between because the analysis of 2D elastic collisions is really greatly simplified. Okay, so more on that later, but for now, let's talk about the center of momentum frame. So, okay, so before that, right, I wrote the conservation of momentum. Now the conservation of momentum equation becomes a vector equation because we're working in multiple dimensions. But there's nothing to fear, right? Because previously your initial your initial velocities and final velocities are just real numbers, right? They can be negative, they can be positive, right? But in this case, what it means to go into multiple dimensions is just that each of these quantities is a vector. So when you have MA UA plus MB UB, right, equals to MAVA plus MBVB, right? This is the 1D version. If I put vectors, if I put arrows on top of these, right, these quantities, these velocities are vectors, right? Then this just holds as a vector equation, which remember, right, what does it mean for a vector equation to hold? It means that all the components are equal. So if I have x, y, z equals to 1, 2, 3, it just literally means three equations, right? It just means x equals to 1, y equals to 2, z equals to 3. So if I decompose these into the individual components, right, it'll just literally be muax plus mbubx and so on, right? It'll just be each of the individual components. It's just that we're packaging it nicely into a column of three numbers so that we only have to write one equation, right? Which is actually three equations in disguise. Okay, so nothing to fear about vectors, right? Yeah, they're just tuples of numbers. So, okay, so with that aside, right, what's special about the center of momentum frame? The center of momentum frame is the frame such that when you observe the objects moving around, right, total momentum is zero, right? And that's also why we call center of momentum frame because we are the momentum, the center of momentum, right, which is initially in the lab frame, the center of momentum is moving. But if we go into the center of momentum frame, then the center of momentum in the center of momentum frame is stationary. Okay, so what this means, right, is best if I illustrate it with an example. So lab frame, right? Lab frame just means the usual frame that we're working with. If I have a 1 kg object moving at 2 meters per second, and a 1 kg object that's stationary, right? 0 meter per second, right? What's the momentum in this case? The momentum, right, is simply 2 times 1, right? So the momentum is simply 2 kg meter per second towards the right, right? So if we take rightward as positive, then yeah, this is the momentum. Um, okay, so this is the total momentum, right? And of course, this one has zero momentum, so it's plus 0. Okay, so you see that in this lab frame, there's some amount of momentum, right? But if we go into a frame, if we go into the center of momentum frame, and what is that, right? That is the frame that is moving rightwards at a velocity of 1 meter per second. Okay, so if we are, imagine we are like, we see the two, in the lab frame, we see the two objects like this, right? They're moving, the left one is moving towards the right one. But now we are zooming towards the right at 1 meter per second, right? If we go into this new frame, then essentially you're going to see the 1 kg object. You're going to see the 1 kg object instead of moving at 2 meters per second. Now you're only going to see it moving at 1 meters per second, right? And now previously this second object on the right over here is stationary, but because now you're moving to the right at 1 meter per second, you are going to see it going leftward at 1 meter per second. Right, so this 1 kg object is now moving leftward at 1 meters per second in the center of momentum frame. And what do we see over here? We see that total momentum, right, is in the CM frame, right? So I'll put comma CM here to emphasize that I'm in the center of momentum frame. Is what is this over here? So taking rightward as positive, right? We have 1 meter, we have 1 times 1 plus 1 plus this one, but it's in the opposite direction. So this is minus 1 times 1, and this is 0. So you can see that in the center of momentum frame, right, which is the frame that's going rightward at 1 meter per velocity, 1 meter per second of velocity in this question, right? In the center of momentum frame, the total momentum is 0. So there's two questions right now, right? One is, how do you know such a frame exists, right? And second of all, how do you calculate the velocity of such a frame? How do you calculate the velocity of such a frame? And both of them are going to be answered by a construction. So the construction is simply you find the velocity of the center of momentum or the center of mass, right? And that's your velocity of the center of momentum frame. So if we this is the proof over here, but basically the proof just involves calculating the velocity of the center of mass, which is just a weighted average, right, of the velocities weighted by their masses. You see this ma over ma plus mb, right? And this mb over ma plus mb is just a weighted average of the object's velocities. Okay, so yeah, so if we substitute equation 84 back into the into the following, then we can check that the momentum is 0. But intuitively, right, if two objects are moving such that, right, if the two objects are moving such that the momentum, right, you're calculating the center of mass or the center of momentum, you're calculating the velocity of it, right? Then if you boost into that frame, then if you calculate the center of mass again, it's not going to move, right? If you calculate the center of momentum, it's going to be 0. Yeah, so that's essentially the idea. So center of momentum frame is a frame such that the velocities are 0. And why is this nice? Right, this is nice because now the momentum equation becomes remarkably simple. Right, previously we had a linear equation, but now um not only it's still linear, but now the UA and UB have a they're just they're just they're just pointing in opposite directions now, right? Because if both of them sum up to 0, right? MAUA plus MBUB sum up to 0, then you rearrange it, you can get that UA is a ratio times UB. And what's the interpretation of this equation? Right? This equation tells me that if one object is moving at some velocity, right, the other object is moving in essentially the opposite direction, but the velocity could be scaled down. So if this is length of, let's say, 5, right, this could be length of, let's say, 3, but they're parallel, essentially. They're parallel, right? And that's for the initial. The final velocities are also parallel or anti-parallel. Right? Anti-parallel just means pointing towards each other, right? And this really simplifies the kinetic energy equation. So just now, right, so far we have just dealt with the center, the conservation of momentum equation. We basically arrive at equations 88 and 89 relating the initial velocity of A with the initial velocity of B, as well as the initial velocity of A, as well as the final velocity of A and the final velocity of B, right? They're just linearly proportional to each other, scalings of the vector with a flipping, right? So it's a flip and a scale if you think of these as vectors. But now the kinetic energy, right, which is just UA squared. So this is just the UA squared over here just means the length of the vector. So if the vector has components, let's say 1, 2, 3, then the length of the vector, right, would be the length of the vector would be square root of 1 squared plus 2 squared plus 3 squared, right? So this is what we mean by UA squared. Okay, so UA squared means the length squared. So the length squared would be this thing squared, which is 1 squared plus 2 squared plus 3 squared. So the kinetic energy equation, right, which is this, it can factorize out nicely because we just established that UA is proportional to UB, right, and VA is proportional to VB, right? So that means that initially we're UA squared plus UB squared, but UA can be expressed in terms of UB, so we get the following factor times UB squared, right? And likewise for the VB squared. And voila, what do we see? We see over here that the two factors are actually equivalent. So the length of the UB squared, the UB squared and VB squared are equal, right? And that means the length of the initial velocity, the magnitude of the initial velocity and the magnitude of the final velocity are the same. And that is really quite remarkable. So what does that mean in the context of collisions? Okay, so we've done the math. Let's explore the consequences of the math, right? The intuition behind the math. Physics is all about doing the math and then understanding what the math is saying, right? So equation 92 is amazing equation, right? What it's saying is that initially I have the two objects going towards each other, right? Like that, right? And after that, after the collision, so imagine they hit each other. They hit each other at the center somewhere around here, right? They hit each other. And after that, right, the final velocity of B, so this is UB, right? But the final velocity of B, one thing is we don't know which direction it is in, right? It could be in this direction, it could be in this direction, it could be in this direction, right? But what we do know is that the length of this VB, right, the length of VB is equals to the length of UB, right, as vectors. So initially this is the velocity at some length, right? The arrow has some length, but after the collision, the length didn't change, right? The direction, we currently do not know any information about it, and it will turn out we actually do not have enough information to figure out the direction yet, right? We'll talk about this in 2D collisions, but what's remarkable is that the final velocity, the magnitude of the final velocity is the same as the magnitude of the initial velocity. And if we do it for A, we'll see that that applies to A as well, right? So UA and VA, they have the same magnitude. Okay? UA and VA have the same magnitude. So magnitude of the vectors, magnitude of the vectors. So that is the remarkable thing about the center of momentum frame, is that if you work through the conservation of momentum equation, right, and the conservation of energy, kinetic energy equation, you just get that the magnitude of the vectors remain the same. Okay, so since this video is getting a bit long, I'm going to talk about next section in the next video.